Hello guys, and welcome to lesson 9C. I can solve problems using properties and theorems about tangents. Well, a tangent line is a line that intersects a circle at exactly one point, and that point is called the point of tangency. So I'm looking at a circle with a center of A and a point B on that circle. There is only one line that can pass through point B that is tangent to it. Whereas if I've got a circle with a center of C and a point D that is not on the circle but outside the circle, there are actually, oh, that was bad. Let me try that again, guys. There are actually two tangent lines that I could draw that would go through B and intersect C at exactly one point, here and here. So there is one tangent line when it's on the circle and two tangent lines when the point is outside of the circle. Now, when I draw a tangent line, that tangent line is going to be a tangent line if and only if it is perpendicular to the radius of my circle. Perpendicular at the point of tangency. So we'd have this situation. So if I therefore have two of these lovely tangent lines, this time they're intersecting at point P, and I draw in the center and the radii, these guys would both be perpendicular. These are radii, so they're congruent. If I were to draw a segment here to make this into two congruent triangles, we can see that by the HL theorem, segments PB and PA are also going to be congruent. So tangent segments to a circle from a point are also congruent. And we kind of just drew this again, but what this means is that in this picture here, again, I draw on the radii and this common side here, it would mean that HJ in this picture would be congruent to IJ. And the reason is that it creates two congruent right triangles by the HL theorem. So by CPCTC says that HJ would be congruent to IJ. So we'd have this shared side, we'd have the common radius, right? The radii are congruent. So by HL, because that's a hypotenuse and that's a leg, these two triangles would be congruent, which would mean these two tangents here would also be congruent. So moving right along to the next page, maybe possibly. Let's look at some examples of how this is useful. So if I'm given two tangent segments, HJ and IJ, and radii GH and GI, and I know that the measure of angle HGI is 38 degrees, so this is 38 degrees, I can now find the measure of angle HGI, which is this angle here. Well, we know that because these are tangents, these guys are 90 degrees. And at this point, this figure here is really a kite. It's a quadrilateral, which means that the two 90-degree angles and that 38-degree angle, plus the measure of my missing angle, HGI, they must all add to 360 degrees since this thing makes a quadrilateral. Therefore, when I add them all and subtract together, I get that the measure of HGI ends up being 142 degrees. So it's one of the ways I can use tangents. Looking at this picture here, again, I've got some congruent tangents. If this is 24, this guy is also 24. That's a right angle. And if I want to find from K to N, well, K to N, if you look, is the hypotenuse of this right triangle, the KLN right triangle. So I can do 7 squared plus 24 squared is equal to KN squared by the Pythagorean theorem, or 49 plus 576 equals KN squared. That's 625 equals KN squared. So 25 is the length of KN. Let's take a look at another example. Here, I know that FP is tangent to the circle and that the measure of angle FPQ is 30 degrees. So this guy here is 30 degrees. I know that E to P, from E to P, that's this whole segment here, is 20. And I want to find FP and I want to find PQ. Well, this is actually a pretty cool problem because if this is a 30-degree angle and this ends up being a right triangle, and in a right 30-degree angle triangle, this angle here is also 60, which makes this a 30, 60, 90 triangle. So it follows the 30, 60, 90 pattern. So this is n, this is 2n, and this is n square root of 3. So if I have 20 equals 2n, divide both sides by 2, I get that 10 is the value of n, which means this side here is 10, and this side here is 10 square root 3. So EF is 10, FP is 10 root 3, and PQ, well, PQ is from here to here. If this is 10, this is also 10 because it's a radius, therefore PQ is also 10. All right, let's look at another example. Here I know that FP is tangent to the circle E, and that EF is 7, and QP is 8, and I want to find FP. Now, if EF is 7, EQ is also 7 because they're both radii, and radii are always equal, which means the length of this side here is really 15. Now, this is a right triangle because the tangent is always perpendicular to the radius, so we can solve for FP, I'm going to call it x, using Pythagorean theorem. 7 squared plus x squared is equal to 15 squared, or 49 plus x squared is equal to 225. So I get x squared is equal to 176 when I subtract. 176 is 2 times 2 times 2 times 2 times 11 when I factor tree it. So when I simplify this, I've got 2 pairs of 2's, so my x is equal to 4 square root 11, and that's my answer. All right. Let's take a look at another example here. Now I have a radius of 3. My radius is 3, so this side here is 3. And I want to find QR. Well, this is a 45-degree angle. This is 90, so this guy must also be 45 degrees, which means this is a 45, 45, 90 triangle. So my side lengths will follow the n square root 2 pattern. I know that n is 3, therefore QR must be 3 square root 2. That one's not too bad. Let's take a look at this guy. I want to find the value of r. Again, I know that this is a right angle. If this is r, this is also r, which means this side length here is not just 8, but 8 plus r, or r plus 8. So when I'm putting this into the Pythagorean theorem, that's the hypotenuse. So we would have r squared plus 12 squared equals r plus 8 whole quantity squared. That's r squared plus 144 equals, remember guys, when you've got r plus 8 squared, that's r plus 8 times r plus 8. You got to do both pieces. So when I FOIL that out, I get r squared plus 8r is plus 16r plus 64 equals, we still have r squared plus 144. And something really nice happens. My r squareds cancel. And I can then subtract the 64 over to the other side. So I end up with 80 is equal to 16r, divide by 16. I get that 5 is the value of r. And if I want to check my answers, this guy would be 5, and this guy would end up being 13. 5 squared plus 12 squared equals 13 squared. I did it right. All right, moving right along. We can say that a polygon is circumscribed about a circle if and only if the sides are all tangent to the circle. We can also say that the circle is inscribed in the polygon. So when something's inside, if a circle's inside something else, we could say that it is inscribed in the polygon. So here we have TUV is circumscribed about circle Z, and I want to find the perimeter of the triangle. Now, I want you guys to recognize that these are all tangent lines. And our party hat theorems, let's go back to our penguin friend over here. Our party hat theorem says that if I've got two segments tangent to the circle at the same point, those two segments are congruent. So looking back at this problem, if this is 7, this piece right here is also 7. And if this is 22, this piece here is also 22. And if this is 21, this piece here is also 21. You've got 3 party hats coming off of this. So my perimeter of this thing is going to be 7 plus 7 plus 21 plus 21 plus 22 plus 22, which when I add all of those together gets me 100 units as my perimeter. We can also have common tangents to circles. So it's a line that is tangent to 2 distinct circles. In other words, the circles have a tangent line in common. So here, this is actually a common exterior tangent in this picture. And I say that BE is a common tangent to circle A and circle C with CD equal to 4. So that's the radius of that guy is 4. And DE equal to 8. DE is equal to 8. BE, that's from here to here, that's equal to 18. And I want to find BA. That's what I'm missing, X. Now, if you look at these guys, they share this angle E. Angle E is a shared angle, and they both have a right angle, which means that these guys, that these 2 triangles are similar by angle, angle, tilde. So I have similar triangles by AA tilde, which means I can solve these by proportion. Since they're similar, their sides are in proportion. So looking at the small triangle, the radius is to that leg, 4 is to 8, as on my larger triangle, the radius, I don't know, that's my X, but that longer leg is 18, X over 4. So now I'm going to cross multiply. I get 8X equals 4 times 18 is 72. Divide by 8, I get that my X is 9, which means that BA is 9. So let's take a look at this one. In this picture, I have what's called a common internal tangent. And a common internal tangent is a line that's tangent to 2 circles that passes through the centers of the 2 circles. So if you see, if I connect the centers, I connected the centers by AE, that tangent line BD crosses that line. So it's considered an internal tangent, whereas this guy up here was an external tangent, right? That's an external tangent because my common tangent did not cross that line. And what this does is it's again going to create some similar triangles because we still have right angles here and here. And now this is a common vertical angle. So these 2 triangles are similar by AA again. So the triangles are similar by angle, angle, tilde. So without even reading the question, I know I've got similar triangles and I will likely solve them with a proportion. So they tell me that the centers, A and E, are 10 units apart. So from here all the way over to here is 10 units. Okay. And we have on the diagram that the radii are 3 and 2 respectively. Now, knowing that the centers are 2 units apart isn't as useful because we don't know how that's distributed. So what I'm going to do is I'm going to break this into, I'm going to call CEX and call from A to C 10 minus X, because if they're 10 units apart, then if I let CE be X, then this guy has to be 10 minus X, that they'll still add to 10. So let's make a proportion. I'm going to look at the radius on top. So if I'm looking at this tiny triangle here, my radius of this triangle was 2. And the part of that central segment for this smaller triangle here is X. Then on my larger triangle, my radius was 3. And that segment that connects the centers on this one is 10 minus X. And now we can solve this by cross multiplying. So I get 3X equals 2 times 10 minus X, or 3X equals 20 minus 2X. Add the 2X over to get 5X equals 20. So I get X is 4, which means that this now splits up into a ratio of 4, where this guy now would be 6. But what I really want is the length of CD, The length of CD is right here in my picture. I know this is there's a lot of ink on here now. Well, I can solve that part using the Pythagorean theorem because this little triangle right here is a right triangle where that 4 we just found is the hypotenuse. So I can do 2 squared plus my missing CD squared is equal to 4 squared and solve from there. So I have 4 plus CD squared equals 16. So CD squared equals 12. I have to take the square root of that. 12 is 4 times 3, so the length of CD is 2 square root 3. All right, we're getting there, guys, and this is a longer lesson. I apologize, but we're moving as fast as we can, I promise. All right, now here's another common external tangent and notice it doesn't cross the center between the two circles, which means it's a common external tangent. And I want to find the length of that common external tangent. If the length of AD is 4 and the length of BC is 3 and between E and F is 2. Now I can fill in more than just what I have, because if BC is 3, then FC is also 3 because it's also a radius. And if AD is 4, then DE is also 4 because it's also a radius, which means the whole length of this piece here is in fact 4 plus 2 plus 3, which is 9. Now, the problem is that what I want is the length of AB, and these guys are both right angles. This is actually made a right trapezoid. And rather than looking at this as a right trapezoid, I'm actually going to split this into 2 figures. I'm going to draw in a new segment. And that new segment I'm going to draw in is going to split this into a rectangle and a triangle. I'm going to split it like this because I'm able to solve for lengths of segments on right triangles really easily. I'm going to if this is 3, I'm going to draw the segment such that this is also 3. And if this whole thing is 4 and this is 3, then this piece now is 1. So I've just drawn in a new segment. Notice it's parallel to this segment, so these pieces here will be congruent. I'm trying to find AB. That red line I just drew is AB. And now I've got a right triangle right here with a leg length of 1 and a hypotenuse of 9, and I'm going to call this guy X. So I can say that 1 squared plus X squared equals 9 squared, or 1 plus X squared equals 81. So X squared is 80. When I take the square root of that, 80 is 16 times 5. So X is 4 root 5. That is the length of that's the length of that common tangent. We do it by splitting it into we split our trapezoid into a rectangle and a right triangle. So we now have another example like this. In this time, I have to draw the picture, so let's do that. I want the centers of two disjoint circles with radii 3 and 6 are 10 units apart. I want to find the length of their common external tangent. So I'm going to start off by drawing 2 disjoint circles. Okay, so I have a bigger one. Ooh, hello. Which I may actually move. A bigger one and a smaller one over here. And they have a common tangent, which we're going to draw. Well, first we're going to join their centers. Their centers are joined. And they have a common tangent, which this is kind of hard for me to draw, guys, but I'm trying my hardest. Common tangent. Ooh, nope, wrong thing. We get the idea. Common tangent. So here we go. Let's draw in everything else. We have centers joined. And we've got our radii. We've got a radius of 6 and a radius of 3. And my length, that the centers are 10 units apart, so this segment here is 10. Just like the last one, I'm going to divide this, what is a right trapezoid, because guys, these are right angles, into a rectangle and a right triangle, just like that. So that what I'm trying to find, this segment here, X, is now this segment here. And if this radius is 3, that means this piece up here is 3. And if all of this is 6, then this down here must also be 3. So my triangle would be 3 squared plus X squared equals 10 squared, or 9 plus X squared equals 100. So X squared equals 91. And when I take the square root of that, it doesn't simplify. So my answer is the square root of 91. And that's all I have to do. All right, last question. So find the equation of the line containing the given radius, then find the equation of the tangent line. Okay, so finding the equation of the line with the radius. So they've already drawn it through here for me. And if you remember, from y equals mx plus b, my y-intercept right here is -3. That means my b is -3. And the slope, if I'm looking at rise over run, the slope of this is up 3 over 4. So my slope is 3/4. So the equation of the radius, y of the radius, is really equal to 3/4 x minus 3. Not too bad, right? Well, our tangent line is going through the point right here. I want to change colors to red. Thank you. The point right here, -4, -6 is the point right here. And we know that tangents are perpendicular to their radii. Well, the slope of the radius was 3/4, and to make a perpendicular slope, we flip it and we change the sign, which means the slope of my tangent has to be -4/3. Now, in Algebra 1, you learned a really useful form of a line called the point slope form of a line, which was y minus y1 equals m times x minus x1. This is all review for you guys. Well, you've got a slope. This is your slope, the -4/3, and you've got a point, -4, -6, so plug it in. Y minus y1 was -6 equals -4/3 times x minus x1 was -4. We simplify this to be y plus 6 equals -4/3 times x plus 4. And guys, you can leave your answer just like that. I don't care if it's an mx plus b form. This is the equation of the line. It's just in a different form. So yes, this is the equation of the tangent line, and this is the equation of the radius. All right, guys, thank you very much. That's the end of this video. And if you have any questions, please come in and see us. Thank you.